Okay, let's dive right into this explainer. Today, we're going to demystify perimeter and area formulas by solving some very real-world mathematical mysteries. You know, if you've ever stared at a math textbook and wondered, when am I literally ever going to use this? Well, you are in the right place. We're going to look at space, geometry, and formulas not just as a bunch of boring letters on a page, but as the hidden code that keeps sports fair, designs perfectly accurate, and honestly, the entire universe measurable.
So here's our game plan for today. 1. The athletics track mystery. 2. Mastering basic perimeters. 3. Circles and the pi constant. 4. Solving the track stagger. 5. Pause and solve practice. And finally, 6. Essential formulas and summary. By following this path, I promise you, those tricky geometry formulas are going to make perfect sense by the end of our time together.
Section 1, the athletics track mystery. We are going to start right at the Olympic starting line with a classic geometry puzzle. Take a really close look at this 400-meter track. Notice anything weird? The athletes lined up for this 4x100-meter relay are definitely not starting at the same line. The runners in the outer lanes start way ahead of the folks in the inner lanes, yet they all cross the exact same finish line. That distance between the starting points of adjacent lanes, that's what we call the stagger. And this visual mystery kind of begs the question, why are they staggered like that? Does this give someone an unfair advantage? Or, honestly, more importantly, how do organizers calculate it so accurately that every single athlete runs exactly 400 meters, no matter which lane they're stuck in? So, to figure out the exact mathematical distance each runner actually travels, we first need to take a step back and understand how we measure the boundaries of shapes. Section 2. Mastering basic perimeters. Before we can solve that track stagger, we absolutely have to master how we measure the boundary of, well, any shape.
Look at these numbers. They brilliantly illustrate that for regular shapes, perimeter isn't just some random addition problem. It's a highly predictable ratio. Imagine a tiny insect walking around the border of a square that has a side length of a. It travels that distance a 4 times, right? Making the perimeter 4a. If you double the side, well, the perimeter doubles too. The ratio of the perimeter to the side stays absolutely fixed at 4:1, no matter how massive that square gets. And for an equilateral triangle, that fixed ratio is exactly 3:1. So really, perimeter is essentially just a constant, predictable mathematical relationship.
And what's super fascinating here is that we can literally see this predictable spatial relationship visually in algebra. You don't just have to blindly memorize the formula for a plus b squared. Just look at this area model. A big square is broken into smaller chunks. You got a square of area a squared, a square of area b squared, and 2 rectangles of area a times b. It perfectly maps out the square of a binomial in a totally visual way. When you actually understand the meaning behind the shapes, the formulas basically write themselves. So, quick recap. Perimeter and area aren't just arbitrary textbook rules. They are fixed, visual relationships tied directly to a shape's dimensions.
Section 3, circles and the pi constant. Now, let's take this ratio concept and apply it to circles to uncover something truly universal.
Just like every square in existence has that rock-solid 4:1 ratio, literally every single circle in the universe shares its own constant ratio between its total perimeter, which, we call circumference, and its diameter. We call this magical constant pi. Whether it's a coin in your pocket, a car tire, or a massive planet, if you divide the distance around it by the distance across it, you will always get pi, which is approximately 22/7 or 3.14.
So, the crucial takeaway is that to find the total distance around a circle, you just use this constant. Since the diameter is just 2 times the radius, or r, the formula becomes circumference equals 2 times pi times the radius. C equals 2 pi r. And remember, that's not just a string of letters to memorize. It's a fundamental rule of how space works. So mini recap. Perimeter is always a fixed ratio, and for circles, that ultimate defining ratio is pi.
Section 4, solving the track stagger. Okay, let's bring this powerful formula back to the athletics track to solve our initial mystery and do the exact math that Olympic officials do. To calculate the true distance an athlete runs in that innermost lane, we break the track down logically into straight sections and curves. First up, the track has 2 straightaways measuring 84.39 meters each. Second, and hey, here is a fantastic exam tip for you, athletes don't run exactly on the painted inner white line. They run slightly outside of it. So organizers actually add a 0.3 meter running offset to the inner radius of 36.5 meters. That gives us an effective running radius of 36.8 meters. Third, we have two curved semicircles on either end. If you push those two halves together, what do you get? One perfect full circle. So we calculate that circumference using our formula, 2 times pi times our new radius of 36.8. Now for the magic. Looking at the final calculation, when you double the straightaways, you get 168.78 meters. When you calculate the full circle for the curves using our effective radius, you get 231.22 meters. Add those two numbers together and boom, it equals exactly 400 meters. Every single subsequent lane has a slightly wider radius, meaning a larger circumference, which is exactly why those starting lines absolutely must be staggered forward. The math completely proves the stagger is perfectly calculated for fairness. Quick recap, by combining straightaways and using pi for the correctly offset curves, we ensure every athlete runs a perfectly fair race.
Section 5, Pause and Solve Practice. All right, now it is your turn to apply these spatial relationships in a simulated exam scenario, because active practice is for sure the best way to learn this stuff.
I actually want you to pause this explainer right now, grab a pencil, and try to sketch this out before I reveal the answer. Imagine a circle with a radius of r, and draw a square perfectly fitted or inscribed inside it, with its corners just touching the edges. Can you figure out the exact ratio of the square's area to the circle's area? Seriously, give it a try. Okay, how did you do? If you calculate the area of that inscribed square and divide it by the area of the circle, which is pi times r squared, the radius variables actually completely cancel out. The exact ratio is always 2 over pi, which calculates out to approximately 0.637, meaning the square takes up about 63.7% of the circle space. Pretty cool, right? Let's take it a step further. Look closely at this next puzzle. It might seem like a bit of a trick. A hexagon's area ratio is roughly 0.827, which is obviously not twice the square's ratio we just found. Actually, it's exactly twice the area of an inscribed equilateral triangle. But the real, absolutely crucial takeaway here is the progression itself. A square covers about 63% of the circle, while a hexagon covers nearly 83%. It's fascinating how just increasing the number of sides of the inscribed shape gets us closer and closer to the actual area of the circle. If you drew a shape with 1,000 sides, it would almost perfectly match the circle. And fun fact, this is exactly how ancient mathematicians originally estimated the value of pi. So, wrapping up our practice session, comparing inscribed shapes to their surrounding circles reveals the fundamental limits and progressions of geometry. Section 6, Essential Formulas and Summary. Let's wrap up our lesson by consolidating everything you need to know to completely ace this chapter. We have covered a lot of ground today, quite literally. Go ahead and take a screenshot of this master formula sheet right now. You've got your pi constant and your circumference formula. Notice that arc length formula? That is literally just the circumference formula multiplied by whatever fraction of this circle's 360 degrees you're looking at. It's perfectly logical. For triangles, you have your standard half base times height. But also look at Heron's formula down there. That one is an absolute lifesaver in exams when you only know the 3 side lengths and don't have the height. And remember, please don't view these as just random letters to blindly memorize. They represent the constant, predictable ratios of the physical universe. Before we go, I want to leave you with a final, really provocative thought. Look at this incredible geometric puzzle. We have a standard right-angled triangle, and semicircles have been drawn perfectly on all 3 of its sides, labeled A, B, and C. Using the formulas we literally just learned for area, and thinking about the basic properties of a right-angled triangle, can you actually prove this beautiful relationship? That the area of semicircle A plus the area of semicircle B perfectly equals the area of that largest semicircle, C? And, how does this mathematically connect to Pythagoras' theorem? I highly encourage you to sketch this out and try to prove it yourself. It's a fantastic way to test your true understanding of what we've covered. Thank you so much for joining me on this explainer. Keep asking those great questions, and I'll see you next time.